All right, good morning and welcome everyone to our CIE overview this morning. Looks like we have a few folks just coming in. I'm going to ask you all to mute yourselves as you join the meeting because you won't be automatically muted. All right, before we get started today, just let you know that you all are welcome to introduce yourselves in the chat and have conversation within the chat. If you're able to use the meeting Q&A, that's a great place to call attention to a question for one of our presenters today. And we'll be monitoring for questions as we go through. Now I'm going to turn it over to Ginger Wright, who will be leading our presentation today to kick us off.
Good morning. My name is Ginger Wright, and I'm part of the Idaho National Laboratory's Cyber-Informed Engineering Program. I am the program manager for this DOE-sponsored endeavor. I've got with me Ben Lampe, who is our principal investigator, and today's conversation is going to be about cyber-informed engineering, but starting with a conversation about engineering risk management. And before we go too deeply into that, George Shea is the author of this conversation and brought us together to have it. So I wanted to recognize George and see if you had comments that you wanted to make to kick us off as we talk about cyber-informed engineering today.
Oh, thank you. I wasn't expecting that, but thank you. And I'm very excited to bring everyone together. I guess in the invite I saw that there's also another meeting that was scheduled. So this will be recorded and everyone else can see it. And it's, again, very exciting to me that we're going to be able to see how engineering really affects the cyber side of things, and the cyber-informed engineering really affects the safety of different systems for a continued resilience, which I've been really focusing on. So I'm very excited. And if I can help in any way on either side, the engineering side or the INL side, please let me know.
Thank you. And in today's conversation, as you put questions in the chat, we will digest them and add them to the flow of conversation or stop at certain points and manage those. So as we begin today's conversation on cyber-informed engineering, we start with this slide, not as an attempt to scare anyone, but kind of as a starting point to say, today's engineering technology, upon which much of today's critical infrastructure depends, is leveraging digital technology increasingly. And that digital technology is vulnerable to adversary attack and adversary manipulation in ways that not only affect the data that might reside on or be transacted by those systems, but can actually affect the critical engineering functions that infrastructure is trusted to perform. There is a gap currently in our engineering education. Engineers are taught to deal with many kinds of risk to engineering undertakings, but largely cybersecurity is not something that they are taught to manage as if it is a standard engineering risk. Instead, they are depending upon cybersecurity professionals. And in our conversation today, we will posit how those cybersecurity professionals, although with tooling that can help protect these systems, they are not fully educated to understand the engineering basis of risk, and they don't have tools that affect the engineering consequences which can occur as a result of a cyber attack on infrastructure that deals with physical assets. And so as this conversation continues, we welcome your questions, we welcome your concerns, and we hope that we have an idea for how to formulate additions to engineering education that can empower engineers to manage the risk of digital-induced sabotage as simply another facet of the engineering risk to their programs, using some of the same tried and true engineering risk management techniques and engineering controls that have been present in some cases for decades. So that's our departure point. Today's conversation will provide an overview of cyber-informed engineering, but we wanted to start with a discussion of engineering, cybersecurity, and operational technology, focusing first on the idea of risk management. And the way that we formulate risk and risk management procedure is based on a formula that is widely promulgated. And that is, risk is the potential that an undesired consequence could occur for an undertaking of significance. We manage this potential by either lowering the probability that that event could occur. And I've got some other synonyms for probability, and there are some reasons I've chosen some additional words that we'll go into as this conversation continues. Another way that we can manage risk is to lower the impact of that event occurring or minimize the consequences, even if that event occurred. So to take this a little bit lower, how we lower risk in engineering, on the probability side, we provide education, training, we provide guidelines to engineers, all designed to address how they can minimize the probability of an undesired event occurring within their engineering undertakings. Modeling helps us predict the places where those undesired events might be likely. Standards help ensure that we are trying to find the least likely avenues for practicing engineering so that we do not invite undesired events. We have requirements and education. On the impact side, where once we've lowered the probability of an event occurring to the extent that we can, the ways that we minimize the impact include hazard analysis that lets us identify where engineering controls might minimize the undesired impacts. We have education that helps us develop strategies for controlling impacts. We use engineered controls to limit what a system or process will do if an undesired event occurs. Some of those things might include manual stops and fail-safes. We issue personal protective equipment. We are dependent largely on processes which are built upon scientific properties, and we depend upon our knowledge and command of those scientific properties within our engineering domain so that we can define what impacts could occur and the controls that would best prevent them. We use material selection and reinforcement as a further opportunity to minimize impacts. And when impacts occur and we cannot prevent them, we use incident response and incident response planning to quickly remediate the damage that occurred and return to critical functions. For each engineering context and discipline, the particular tools for lowering probability and impact may vary, but generally speaking, this list gets at some of the techniques that we use in engineering. Modern engineering occurs today across multiple domains. Engineers typically manage risk in the physical domain, which includes understanding impacts to reliability, safety, the performance of the process that the engineering is governing, and understanding and controlling the quality of outputs to occur as desired. Cybersecurity manages risk in the digital domain, often controlling impacts to the confidentiality, availability, and integrity of data. If we move our conversation to risk management in cybersecurity, things change a little bit from how risk is managed in engineering. First, this word probability. It depends upon having an event sequence which can be probabilistically modeled and estimated. And in cybersecurity, because there is a human adversary at the root of any desired impact, we are no longer working through a probability assessment. Instead, we move to likelihood, which for those who do probabilistic modeling is not as comfortable a place. The mathematics is not as good there. Additionally, when we think about impact on the cybersecurity side, we are thinking about the data or digital domain versus the physical domain. Often the physical domain is outside of the context that a cybersecurity professional may command. For lowering the likelihood of a risk in cybersecurity, cybersecurity professionals employ some of the similar tools that we have in engineering, education, training, guidelines, the things I've left here in black. Additionally, they add a set of tools, and I've captured a few of them. There are more, including network segmentation, vulnerability management, authorization and authentication, and encryption. And those obstacles are designed to lower the likelihood of an adversary being able to penetrate the digital domain and function within it. On the impact side, there is another set of tools, including logging, network segmentation, vulnerability management, asset inventories, and encryption, and others. And these tools are designed once an adversary does penetrate that digital domain, because we're dealing with likelihood, which we cannot reduce to a probability of 0. These tools prohibit that adversary from performing any undesired functions with what they have, or enable the team at the very minimum to understand the impact of what data might have been taken or subverted and respond effectively to it. There are these tools, and how to apply them are covered for cybersecurity professionals in the standards like the NIST cybersecurity framework and other cybersecurity standards that cybersecurity professionals apply. Moving to a conversation of cyber-physical risk. This combines these domains again. First, we have engineering, which of course happens in the physical domain. We have cybersecurity, which is the digital domain, but through this digital domain, the engineering can be affected. So in this image, we are showing how adversaries can seek to impact the digital domain, in which case cybersecurity tools may lower the probability or the impact of their success. When we talk about cyber-physical risk, often those adversaries are seeking to impact the physical domain through the digital domain. And as a result of this impact, now the tools that lower the probability and the impact of this cyber attack actively move to the left so that they lower the impact of something happening in the physical domain. And I'm going to depict that for you on our next slide. So in the cyber-physical risk domain, the cyber domain is the gateway through which an adversary affects the physical domain. And in that, all of these obstacles that our cybersecurity professionals put to either lower the likelihood or probability of a cyber incursion serve to lower the likelihood of that incursion to affect the physical domain. And so you see all the things in green that I've put on the likelihood side. We can control likelihood by affecting that data domain and making it difficult for an adversary to traverse. However, as we discussed before, we cannot lower this likelihood to 0. And so for an advanced adversary who is capable of moving through the data domain to affect the physical domain, the cybersecurity tools that are left which protect the physical domain are very limited. They include vulnerability management and asset inventory. They include incident response, which of course then means an adversary has had an impact and we are responding to it. But these tools are not incredibly effective. What we would like to be able to empower engineers to do is to come back with engineering design, engineering reasoning, and engineering risk management and protect this physical domain using the same tools we discussed before, including fail-safes, engineered controls, manual stops, but employed thinking about the adversary that comes through the digital domain to impact their physical domain. Today's practice has an engineer thinking about the physical domain and ceding complete authority and decision-making over that cyber domain to a cybersecurity professional, which works well to lower the likelihood of an attack, but does not provide the tools necessary to ensure the safety, reliability, performance, and quality of the function if it is affected on the physical domain by a cyber adversary. So I'm going to stop here and take a look at the chat to see if there are any questions. And then I'd like to tell you a story about how this manifests, because we've talked about cyber risk and its connection to the physical domain. And one of the most compelling stories that happened in the last several years that illustrates this connection happened for the Colonial Pipeline Company. In this event, of course, Colonial Pipeline services the East Coast with a number of products. They provide these products through a pipeline infrastructure, and it is always on, it is always operating. It is a highly engineered system that is designed to deliver the products and services that Colonial's customers need safely, reliability, as desired, and with quality. So the story that I have to tell you about Colonial begins on the cybersecurity side, actually in their information technology portion. In this, a ransomware attack took hostage business data. It encrypted it. And that affected, of course, the business functions of the Colonial Pipeline Company. As Colonial explored the ramifications of the business functions that were affected by this adversary, a data file attacked by the adversary was a key component in understanding what products were flowing through the pipeline and when a given customer might tap the pipeline to access the product that was designed for them. Without that data file, all of their operational functions, heavily dependent upon engineering, could not continue. And the company determined, out of an abundance of caution, to ensure safety, to ensure reliability, so that their performance would not be negatively impacted, they elected to halt operations. So I'm going to walk through this again. We had a cybersecurity issue where the cybersecurity protections designed by the information technology, the data domain protection teams were penetrated by an adversary. As a result of that penetration, engineering and operations functions were affected. It is this lack of engineering risk management brought into the cybersecurity defenses that caused this opening. If engineers had had a chance to assess where do our engineering operations depend upon information technology files, their training and their engineering risk management sensibilities would have quickly discovered that critical interdependency. But because those networks and those interdependencies were solely protected by cybersecurity and information technology priorities, the information or the engineering priority was overlooked. Because of this, we propose cyber-informed engineering as a methodology to bring this engineer an understanding of how cyber risk may affect engineered systems. Cyber-informed engineering was created to use design decisions and engineering controls to eliminate and mitigate avenues for cyber-enabled attack. Instead of being designed for cybersecurity professionals, this is focused on engineers and technicians, leveraging the skills and capabilities that an engineer brings to the table to add defenses that protect the physical domain from impact of cybersecurity. It does not replace cybersecurity, but instead allows the cybersecurity and the engineering to work in harmony, with the engineering setting priorities for where there are dependencies upon cybersecurity protections to ensure safety, reliability, performance, and quality, and allowing the cybersecurity team to lower the likelihood that those variables would be affected, while the engineering team can focus on lowering the impact should an adversary get through and manage an effect on the physical system. Cyber-informed engineering developed a national cyber-informed engineering strategy directed by the U.S. Congress in 2020. In that strategy, the Department of Energy assembled a core set of experts, and they outlined cyber-informed engineering concepts. They also defined 5 integrated pillars that they recommended the Department of Energy incorporate so as a strategy to apply cyber-informed engineering across the nation. The strategy was issued in 2022 and has since been named in multiple administrative documents. The 5 pillars for cyber-informed engineering advocated by the strategy include awareness. First, to share an understanding of the engineering risk management's place in cyber protection of critical infrastructure. Second, to embed these ideas into formal education, training, and credentialing for engineering to ensure that the modern engineer can incorporate digital risk planning, cyber risk planning, and adversarial mitigation as a part of their ordinary engineering risk management, using the same tools and techniques that are taught to engineering professionals today and again have been for decades. They recommended the development of a body of knowledge to help practitioners apply cyber-informed engineering to specific implementations and within specific engineering context, because, as you all know, in engineering, context is critical. They then recommended that cyber-informed engineering be applied to critical, important infrastructure, and as Department of Energy is often the researcher of first resort and the responder of last resort, they recommended that as the DOE conducts research and development calls, that they incorporate cyber-informed engineering principles into the research that all of their energy technology proposals create. As the body of knowledge for cyber-informed engineering was created, the strategy coalesced around 12 cyber-informed engineering principles, and we'll talk about these in details today, but I'll go over them in brief. The first and most important is consequence-focused design. And the key question that an engineer considers in this process is, what are the critical functions my system must ensure and the undesired consequences it must prevent? This is standard engineering thinking. The second principle is engineering controls. How could I, as an engineer, implement controls that reduce avenues for attack or the damage that could result? And what engineered controls would be most effective for my system to guarantee its functionality, but to limit what an adversary could accomplish through data? In secure information architecture, the engineer considers where important data is created and passes through the system. Where could an undesired manipulation of important data cause a change in the actual process that would be problematic? And what controls should be put in place to prevent that manipulation or to detect it if it occurred? With design simplification, the engineer is asked to think about what features, especially the digital features of a system, are not absolutely necessary, and how the engineer could plan to reduce complexity. In layered defenses, the engineer works in tandem with cybersecurity and other defensive teams to create a layer of system defenses that begins in the cyber domain potentially, but is complemented by a set of engineering protections which exist in the physical domain. With active defense, the engineer plans how to proactively defend the system from a threat. If there is a cyber threat, how can the engineer design the system so that both operators and cyber practitioners are involved in that defense and are working to obtain or working to accomplish the same objectives? In interdependency evaluation, and this would have been very important in our colonial pipeline example, the engineer understands where where their system could impact other systems or be impacted. Through this analysis, that colonial pipeline team would have quickly identified the inventory file that was a key dependency and would have been able to advise the cybersecurity team of that file's singular importance to operations and the need to incorporate additional protections on that key linchpin component. With digital asset awareness, the engineer considers where digital assets are used within the engineering function, what capabilities those systems could be capable of, especially if misused by an adversary, and what assumptions the engineer makes about how they work. Often our engineers employ digital technology optimistically, assuming that technology can only be used in the ways that it is designed to be used, and that somewhere in the design of those systems that protections have been put in that would prevent any misuse. And in that, the engineer with additional thinking might be able to question those assumptions and design more appropriate protections, particularly within the context of an engineering process. With cybersecure supply chain controls, the engineer turns their attention to all of the vendors and service providers that manifest security within their engineered application, and particularly those that are interfacing in some way through that digital domain. The engineer thinks about how they will ensure that those providers deliver the same security that the engineer is embedding into the design of the work. In planned resilience, the engineer thinks about how to turn what-ifs into even-ifs, incorporating the advice of the cybersecurity team, but thinking always in the engineering context of what would be the most critical issue that the system could face, especially through cyber attack, and how could the system be resilient to any digital incursion that an adversary might present. With engineering information control, the engineer thinks about how to manage knowledge about the system and how to keep that knowledge out of the wrong hands, considering avenues including procurement, and other ways that information about the system which may aid an adversary to launch a digital attack or may speed them in their ability to highlight which critical engineering functions might be susceptible and consequential for attack. How would they keep that knowledge out of the hands of adversaries to ensure that it is as difficult as possible to launch a knowledge-based attack against an engineered system? Finally, cyber-informed engineering principles are based on a cybersecurity culture where the engineer helps to ensure that everyone involved in the system performs their role aligned with the security goals, so that a misunderstanding about a critical function about the system or how the organization is depending upon that system to work doesn't undermine the careful engineering that has been done. These principles form a what? A knowledge area that can be applied. The application of that principles is in turn done through standards. I've shown some application methodologies here, including IEC ISA's 62443, the NIST cybersecurity framework. However, any engineering standard may perform a basis where an engineer can consider not only the physical domain, but how choices made about that physical domain may strengthen or weaken the system if it is then subverted by an adversary. So the application of CIE is done through existing standards augmented to aid that engineer in thinking not only about the physical, but also about the digital risk. I'd love to tell you a story about how this works in practice. And I recognize that you are all here expert in different engineering disciplines. And for many engineering disciplines, a non-practitioner imagining at detail what's happening within the systems and processes that you reason about is not armed to have a great experience. And so in this case, our story is built upon water. Most of us have experience with water. We understand its properties, and we understand how water flows through systems and is distributed to serve our needs. So in this example of cyber-informed engineering, I'd like you to join me at a municipal water operation. And in this case, we're focused on the water booster pump stations. These stations work within a system of pipes and pumps that operate through a municipal location, ensuring that water is always under the right pressure to flow through the system so that any subscriber of the system, when they operate, their feed can get the right flow for their application. Typically, these water booster pump stations retain pressure in the system, and they also test the water as it flows through and often have the ability to apply chemicals that ensure the safe distribution of that water. In this case, for our water booster pump station example and our municipal utility, we have an opportunity. Today, we monitor our water booster pump stations manually, sending engineers in trucks to control the pumps and to ensure that the system is operating optimally. We have an opportunity through a grant to invest in cloud-based monitoring and control, which is exciting to us because it means that we can maximize the value of our engineers planning new additions to the system and less traversing the system and doing the manual controls. We recognize that this adds cybersecurity risks, but the ability to operate our system remotely is worth at least considering this grant and trying to work through those risks. So because this system is a digital system, the first advisors that we call are our cyber advisors. And I've got a list of the things that they do, but in short, our cyber advisors evaluate both the tool developer for the solution that we're thinking about for monitoring and control, and the cloud provider who would then dispense that solution connected to us. And as a result of the review, they find that the tool developer and the cloud provider are exceptionally skilled and are providing a high quality system as it is judged in the digital domain. We validated with our information technology team that the application of this system to our digital infrastructure is not going to require significant changes. It works well with the security solutions that we have and the digital operations that we already have in place. So when we come to our organizational review board to evaluate the decision to move ahead with this system, our finance and accounting team is in favor because it reduces cost. Our information technology team is in favor because it aligns with our existing digital solutions. And our cybersecurity team is excited because this is a high quality digital solution. However, our engineering and operations team have some questions about how the system will impact how they perform work and how the system might have the potential to bring an adversary far closer to their engineered system. And they request permission to consider the system through the lens of cyber-informed engineering. And I'd like to walk you through how they perform that analysis. As they consider the first principle, consequence-focused design, which has, of course, the key question for how do we understand the critical functions the system must ensure and the undesired consequences it must prevent. Our team first assumes that an attacker defeats all of the careful security controls that the cybersecurity team was so excited about, and that the adversary is then able, through the digital domain, to take physical control of this system, almost as if they were physically within the water booster pump station. And they consider, what is the worst that could happen if such a thing did occur? How would engineering and operations respond? And would any of these issues be catastrophic to the function of the system? They identify that certainly having an adversary control one of the pumps could be a problem. The adversary could turn a pump on when it is supposed to be off, or off when it is supposed to be on, or leveraging that capability, they could then turn the pump on and off and on and off so quickly that it either creates a water hammer effect from overpressuring the pipes within the system and eventually damage, or that it could burn up the pump so that it would no longer operate. And those two things would affect the reliability, performance, and safety of the system. And those things could result in catastrophic impacts. As they consider this, certainly the potential that an adversary could damage the pump station or a pump were of most issue as they thought about their consequence-focused design. Armed with that consideration, they thought about engineered controls. How could they implement controls on the engineering side to reduce avenues for that adversary to either formulate an attack or the damage that could result? They evaluated that the cybersecurity team had identified all of the potential attack reduction options, but the damage reduction options were up to them. They thought about what an ideal control might be. They would like it to be deterministic, governed by physics, so that the digital adversary couldn't take digital control over that control. They wanted to make sure that it was not networked or digital, so again, out of frame with an adversary. Ideally, that its function was visible within the infrastructure. It could be seen and they could use engineering logic to predict how it would operate and what it would do, and that it would be complementary with existing protections. It wouldn't force the system into another potential frailty mode. And they considered, given that description of a control, what they could use that might protect the consequence from occurring. In this case, they identified that a time delay relay, a system that is programmed using the switches as shown, that opens once every time period to accept a command and execute that command, and then does not open again until the time period is elapsed, could be an ideal control. With that control, the adversary seeking to operate the pumps quickly, turning them on and off and on and off and on and off very quickly to cause either burnout of the pump or the water hammer, would be subverted. They could not operate the pumps any faster than the time delay relay's opening window because each command would have to operate only as fast as the relay would allow it. They also evaluated the potential that such a relay, if it had a time delay of once every 30 minutes, would impact operations negatively. Would there be an issue if an operator could only operate the pumps every 30 minutes? And looking at their procedures and operating direction, they determined that a once every 30-minute pump adjustment window was comfortable within their operation. And with this engineering control, they resolved that if an adversary could get through those engineered or those cybersecurity controls and take access to the pumps, that adversary with the time delay relay would be limited to operating those pumps on or off once every 30 minutes or appropriate time window. In that time, the operators could return manually to the pump station, take it offline from the digital system, and operate it manually until the issue could be resolved with the cybersecurity team. They identified this as a highly promising engineered control. They then considered the information architecture of the pump. Where are the data elements in this system where a manipulation of data could have the most impact? Where could manipulation of data lead to loss of protection, loss of safety, loss of productivity and revenue, or damage to property? And how should the potential for those specific operational impacts inform the cybersecurity strategy? In this case, because of the application of the control system simply to the pumps, they identified that setting the pumps, turning them on and off, and changing the pump's operational configuration were those key pieces of data, and that additional monitoring might be needed on the cybersecurity side to detect any unexpected operational commands and raise an alert to the operational team that would allow them to respond as quickly and at the same time as the cybersecurity team might respond. As the group thought about design simplification, considering what features of the system were not absolutely necessary, they identified that when the pump station was created, the team had considered a network-connected variable frequency drive controlled pump. And this was exciting because it would have allowed greater control of the pump and an absolute to the decimal point assurance that the pump was providing specific pressures. But the team had, in the construction of the pump station, performed a feature trade-off and had determined instead that a relay-driven pump was both cheaper and more effective for that operation. As this team now was adding cloud-based monitoring and control, they very much appreciated the earlier design decision to limit other digital functionality so that their focus could be simply on the potential ingress for this one system. So this relay-controlled pump in the original design of the water booster pump station was very much in their favor and limited the complexity of the design that they needed to think about. When the team considered layered defenses, they identified how cybersecurity could prioritize the defenses from the company's side and what they might need to talk to the vendor about that might raise the potential that operations could detect or prevent this activity from occurring. They talked to the cloud vendor about how commands were transmitted and whether the cloud vendor could put in monitoring that might capture an undesired command coming from the system to a pump station and hold it, and whether that might be a good layer of protection. They thought about how many layers of protection they could assemble, both, again, in the water booster pump station assembly, within the networks for the municipal water utility, and on the side of the vendor cloud provider. They created a specific set of requirements so that they could talk to the cybersecurity team about the specific adverse engineering consequences that they needed the cybersecurity team to specifically protect, and how they would leverage both the engineering defenses and the cybersecurity defenses to create the greatest set of engineered defense. As they considered the active defense principle and how they might proactively prepare to defend their system from the threat, they again considered this idea of an adversary turning on and off pumps that today led to the worst engineering consequences. They thought about how they would defend against that actions. What specific things would their team need to do, and what capabilities would they need to ensure that they had the right defenses? They talked about what they would expect of the vendor and how the engineering team and the cyber team would work together. They then thought about how they would document and practice that defense. In this case, they determined that they needed to ensure at all times, within a period of 2 hours after they had done some modeling and figuring, any team needed to be able to respond to a water booster pump station and be able to take it offline and operate. They defined a procedure once that process had been initiated to check in with all of the other water booster pump stations and determine if the threat was significant enough to take the entire system offline. They talked to the vendor about how long they could manually operate their water system and how quickly they needed the vendor to perform cybersecurity remediations in the event of an attack. They identified that they did need an additional contract for staff qualified to do to do manual operations of the pump stations when necessary. They talked to the cyber team about how quickly they might need alerts if the cyber team determined that there were unexpected activities or anomalies occurring in the data side so that the engineering team could respond. And they determined a set of exercises to be performed so that they could regularly practice their defensive activities. All of this they documented into the system design plan. They then looked at the interdependency evaluation principle and thought about how the cloud service and software was a new interdependency for ensuring that the municipal residents received safe water. They thought beyond a specific cyber attack, how might an instability in this new cloud service that the engineering system was dependent upon affect their operations? What would happen if the service went down? And in this case, they determined they could function for 30 days if the system went down, but at that point, they might need swift contracting authority to replace it, and they might need the procurement team to identify a potential alternate system that could operate in the case that this company went out of business or was deemed no longer a viable provider. They talked to the procurement team about that and set plans in motion. For digital asset awareness, they considered where digital assets were used, the functions they were capable of, and their assumptions about how they worked. And in this case, first, they had just assumed that the security provided by the cybersecurity team was enough. But after they did engineering considerations and evaluated the time delay relay, it was important to add that control. They had also originally talked to the vendor about extending the product to allow remote control of the chlorinator. They identified that they were used to operating it manually and thought about how the use of digital technology might change that engineering risk. When they considered that, they thought about whether the process of actually dispensing chlorine in a digital system, how is the amount of chlorine set? It's no longer a screw that you turn that controls an analog amount of chlorine that's allowed in some sort of chamber. Instead, it's a number, and that controls a valve that's open for a period of time and then closed. And they talked to the vendor about if they chose to implement that functionality, was the dispensed amount within the system hardwired? Or is it adjustable in some way? Could an adversary who had access to all of the memory in the system adjust that number so that the system could dispense more chlorine that was expected? And could that potentially be dangerous? They talked to the vendor about, or they evaluated for themselves, if they did this digital chlorination option, how they would know if the product was actually dispensed and how much was entering the water system. Was there some way to link up the digital dispensing of chlorine and the manual work that they were doing to monitor the chemicals within the system? And how might the monitoring indicate for them that a problem had taken place in the digital system? When they evaluated cybersecure supply chain controls, they identified that the cybersecurity and IT evaluation of the vendor and the cloud company were both very mature and well done, but there were still some questions that needed to be asked. Any digital system operating in an engineering environment will have a need to be patched, which potentially threatens engineering operations. So they had questions about how the system is patched, how patches were delivered. Could the asset owner accept or reject the patch? Could the engineering team set a timing so that patches and then the resulting system uncertainty were only applied during times when it was within an engineering window to be considered? And how might the engineering team then advise the cybersecurity team about whether a patch should be applied? Is access allowed to the software vendor or the cloud provider that might ultimately allow control of the pumps, because for the engineers, that's not tolerable and that's not desired. But that question had not really been asked through the cybersecurity team. They had questions about, in that event, how are third-party support providers, including the call-in support, qualified and vetted? These individuals might learn a great deal about this municipal water company's systems, and they had no insight on what that employee might do with that data. Certainly, the engineers would not have answers to all of these questions, but because they are where the operational risk lives, they were the ones who needed to identify the questions and move them into the cybersecurity team that could consider them. For the planned resilience principle, the team began to think about what were the digital what-ifs of the system. What if an attacker turned on all the pumps within the system, or turned off all the pumps within the system? How quickly could the engineering team respond, and what would they do in that case? Certainly, the cybersecurity team would work to get the adversary out of the system. Certainly, the cloud provider would do that, but the water must flow 24 hours a day, 7 days a week. The engineering team must have a plan for that cyber adversary. What if the application vendor reported an adversary attack and there was uncertainty about how that attack might manifest on the municipal company's systems? What if the application simply stopped working? How might the engineering and operational team respond to that event? What if the cloud vendor had ransomware and some of the municipal water company's data or their control scheme was taken away or potentially was owned by an adversary? They considered all of these questions and put in resilience plans. For the pumps on and off, they determined manual operations were effective and predicted very little engineering risk resulting from that scenario. For an adversary attack on the application vendor, which could at any point affect the municipal utility, they determined that they would again return to manual operations and keep a contract vehicle to ensure that they could staff that for up to 2 weeks. If the application stopped working, again, they would use manual operations, and after 2 weeks, they would need to arrange for emergency staffing to continue work on the water system. Ransomware, they identified, had the same answer. But with this thinking about the engineering impact of cyber risk, they were able to inform the financial team about planning for these events and the procurement team about risk mitigation measures that should be put in place. Through engineering information control, they identified that much of information about the upgrade was going to be shared. They were a municipal water utility after all, and any activities they performed with public money are public record. So they went through the system plan and identified for leadership at the water utility what information was reasonable to be shared and what should be withheld from the public for reasons of system security. This ensured that leadership knew what to say and what not to say and did not enable the adversary with critical information. In this case, they determined that the specific vendor, product name, and the name of the cloud vendor should be kept out of the public record so that an adversary wasn't enabled by having this information easily available. When they thought about cybersecurity culture, this idea of ensuring that everyone involved with the system can perform their role aligned with their security goals, they were excited that engineering was invited to drive the implementation of this cloud-based system based on the potential impacts of the cyber attack to engineering certainty. That was a major change within their water utility, and it allowed them to identify risk management mitigations that were appropriate for engineering, but if only the cybersecurity of the system had been considered, would never have been thought about. They identified, as a result of this process, the functions in their organization that were critical to their security, including informing leadership about what key elements to keep private about the acquisition that was created. They identified that procurement would be a key partner in the engineering certainty of the system in the future, and that each of the contracts and provisional ideas that they had about resources, they needed to ensure that procurement filed those and was ready to implement those as needed. I'm going to pause for a minute in case there are questions. We have just walked through an application of cyber-informed engineering to a water booster pump station example, admittedly a very simple engineering problem, but a real one, and one that is faced by municipal water utilities every day. And although this problem was about pump stations and, again, a very specific, narrow engineering consideration, these kinds of reasoning can be done for any engineering application in any context where digital systems are involved. You've worked through each of the principles and you've seen how they put forward the engineering risk that is introduced as a result of adding digital technology through and that cybersecurity vector. So before I go back to talking about cyber-informed engineering, I would welcome your questions if you have any. Okay, I'm moving our conversation forward into how to get involved with cyber-informed engineering. If you find this idea interesting and compelling, as a result of the Department of Energy's investment, we have communities of practice that meet and working groups that meet on a regular basis. On a quarterly basis, we have a cyber-informed engineering community of practice. That is a multi-stakeholder team that we discuss strategy and programmatic activities with and obtain their advice about what is important and what to pursue. Because of the pillars that were identified by the strategy team, we developed 3 working groups. And these are kind of hands-dirty groups that work on products focused on applying cyber-informed engineering in engineering and cybersecurity standards, raising cyber-informed engineering to application through curricula so that it can be applied in both university and technical education. And then we have an implementation working group that is developing the body of knowledge through which cyber-informed engineering can be practiced. And to take a moment to talk about our progress, I did want to highlight the educational institutions that are already working with us to implement cyber-informed engineering into their engineering education. If you have questions about cyber-informed engineering or its application, we can help link you to practitioners at these institutions who can give you advice on how this is working, where they see the limitations, and what they're excited about. I'd then like to take a minute to highlight the body of knowledge that has been developed to date. We mentioned the cyber-informed engineering strategy, and I have it here, and I'll distribute these slides to all who registered. We also developed an implementation guide for cyber-informed engineering. This guide, informed by the V model, takes a practitioner through system concept, requirements, design, development, operation, and even through retirement. And at each step, allows that practitioner to consider cyber-informed engineering questions for each principle that may affect their system at that particular development phase. By considering these questions, the engineer can mature the system and incorporate cyber-informed protections. We have developed a benefits quantification methodology. To expand engineering practice, there must be a rationale that doing so in some way, importantly, lowers risk and raises benefit for the financial investor. And this benefit quantification methodology is a first step at exploring how to define the specific benefits that cyber-informed engineering allows to any system that it is practiced on. We've developed targeted guidance for research and development programs that goes where the implementation began, but focuses the questions on a conceptual idea, something that may not actually be built at full scale, but may be under development or only at the pilot phase. We developed guidance that links cyber-informed engineering to the idea of CWEs, those systemic weaknesses that occur in operational technology systems. We've developed a web-based version of our implementation guide to make that more active and to allow practitioners to interact with the questions and put their answers in and allow a team to perform the cyber-informed engineering reasoning together. Importantly, we've developed two specific tools, and I'd like to invite Ben to talk about these for a minute, that apply cyber-informed engineering in very specific engineering energy domains, one for microgrids and one for battery energy storage systems. And these systems or these tools aren't designed to be an exhaustive engineering examination, but are instead designed to allow practitioners to get to an 80% answer of where there might be an opportunity to increase resilience or operational and engineering surety by applying additional protections. Ben, would you like to talk about these?
Yeah, absolutely. So just as Ginger is mentioning, these analysis tools allow you to focus on specific energy system context. So in the case of a microgrid, knowing that a microgrid is a collection of various energy sources, it provides kind of from a reference architecture baseline, the ability to walk through various questioning modes in the attempt to identify opportunities for those engineered controls, those key controls that engineers can contribute in connection with your traditional cybersecurity controls to really round out that protection scheme used in our modern systems, so that, as Ginger has made mention, we're benefiting from both the likelihood reductions that cybersecurity is able to provide, but more importantly, those physical impact reductions that engineers are chiefly positioned to provide for our modern systems, so that even if an adversary attacks a system, a certain level of performance, safety, or reliability can be maintained throughout that life cycle of that system, which I think is kind of the overall goal for a successful critical infrastructure that we're all desiring, both as in our community, but also as a kind of a national security imperative. So, Ginger, I'll hand it back over to you.
Thanks, Ben. And I'll add that these tools might be a great exploration point for the application of cyber-informed engineering in your specific engineering domain, and maybe a good departure point to help reason through how the practice would actually work. We've developed a set of workbooks to provide an introductory exposure to cyber-informed engineering for energy professionals. And because we are Department of Energy funded, that is our priority. So we focused on microgrids, substations, advanced distribution management systems, and a number of other applications. For our goal 2, and again, Ben, I'm going to hand this one to you. We've made a significant number of advances in the goal of teaching cyber-informed engineering principles at leading U.S. engineering universities. Ben?
Yep. So engineers go through curriculum, and obviously curriculum is a hot topic because it's already packed full in a lot of engineering colleges. So my background is electrical engineer, and I can think back through my curriculum, and I struggle to see how an additional class may be added. And so the approach we took in our curriculum guide, knowing that CIE is meant to describe how engineers can interpret these modern challenges, this really helps engineering universities, engineering curriculum to look at ways to reinterpret a certain activity or a certain lecture, or insert maybe a CIE module or a CIE class, or even go up to a CIE certificate, understanding that every university really has a different appetite or a different ability to implement CIE, all the way from a single lecture up to a certificate. But this provides guidance to empower those curriculum designers to figure out what makes sense for them, and to provide examples, provide baseline learning objectives, those type of things to help guide that journey for a university program. And as you saw in that map before, there's quite a few institutions that have adopted that guide and have started to implement that in various ways. And you'll see various perspectives in that guide and how that's being accomplished. The quarterly webinar, very synonymous with what we've been talking to you today about. We walk through that CIE 101 experience, fashioned around that water booster pump example, because that example allows someone to put their head around it within an hour, unlike other more complex systems where, in order to visualize that, may take much longer than an hour. So that helps kind of engage people initially about what is CIE. Just like we have with the workbooks up in the Goal 1, the Goal 2 workbook provides both the workbook as well as the presentation, the answer key, so that especially those that use this in their curriculum have both sides of the equation, so that when they're leading the discussion, they know where they may want to shoot for in that discussion, a lot like what you saw today. And then finally, that last report, in connection with the guide, goes into greater detail all the various universities and how they're applying CIE since last year. And obviously we've had quite a large growth even into this year. And so this provides a limited set about what everything that's happening in our university systems. I'll hand it back over to you, Ginger.
Thank you, Ben. The third goal resulting from the CIE strategy was to incorporate cyber-informed engineering to international digital design and engineering standards. And in support of that goal, we've developed a requirements analysis framework to be used to think about how to incorporate cyber-informed engineering into engineering requirements documents. We developed a tool for linking the application of cyber-informed engineering to an entity's enterprise risk management function. This ensures that the priorities that are identified for CIE attention are those things that are most important to the ultimate institution's function. We've also developed methodologies for validating that the protections designed in as a result of CIE considerations work as expected and don't unduly expose the process or the function to frailties that CIE then created. In support of outreach and growing the community of practice, we are regular speakers on cyber-informed engineering and would welcome the opportunity, if it fits your needs, to speak anywhere where this idea might be compelling that you know about. Our communities of practice have 290 members, and our 3 working groups have met 32 times over the last several years. We're also developing a set of cyber-informed engineering success stories. How has the application of cyber-informed engineering made a material impact on critical infrastructure? And we are compiling those as they exist, or as they exhibit. But I'll say the water booster pump station example is a real CIE success story, where a company was able to help a municipal utility faced with a very promising opportunity to invest in cloud technology, to respect their engineering risk management processes and make the right decisions that didn't open the engineering systems up to the potential of cyber-delivered attack. I'd like to give you a brief synopsis on what we're working on in FY25 and an invitation that if you see gaps in this approach or something that, especially with your role in ABET, that you would most suggest that we do, we would love to have that insight from you. For the goal one, our goal one in FY25 is using cyber-informed engineering to improve energy sector resilience. We're working on a CIE adoption pathway for asset owners or practitioners who choose to adopt cyber-informed engineering. Is there some way, perhaps modeled after the cybersecurity maturity framework, that they can begin to apply it, and a direction for how they should apply it first? What should they look at first? And then how do they grow to full maturity? We're examining how cyber-informed engineering can be built into procurement strategies. Certainly, effective procurement is a core partner for engineering resiliency, and we want to make sure that we think about how to build these ideas in so that our procurements echo the cyber-informed engineering strategies that our engineers put in place. We are looking at how cyber-informed engineering could affect network sensing for critical infrastructure applications. Think of this as the engineer coming in to tell the cybersecurity people exactly where the most important places to monitor and the most important conditions to monitor for from an engineering perspective, so that where the network people may be tempted to gather all the data, the engineering teams can prioritize what commands, what activities, what timing, what anomalies might be most consequential when thinking about the critical infrastructure system. If the idea of engineered controls attracted you and you began thinking in your context about where those might exist, we are creating a database for engineers who might want to consider, would pipe diameter be an effective control to ensure that an adversary could not pump too much of a chemical through a system and ultimately affect safety? We are creating a database of such controls so that engineers can consider and accept or reject those controls that might make sense to limit cybersecurity risk in their engineered systems. We're looking at how to apply cyber-informed engineering in model-based systems engineering so that these principles are designed into a system even as it is first created. And the modern tools that we use to design engineered systems help an engineer consider these and apply these effectively. We are looking at how to apply cyber-informed engineering to process control and optimization, and how to apply it to process automation. Also, we are looking at CIE-based control and optimization algorithms. In the power systems, there is an idea for conservative operations. When the environmental conditions potentially threaten the reliability of a power system, an area can move into what is called conservative operations. And in that mode, they have different operational conditions. They may staff differently. They may have different cost basis and different procedures. And we would like to explore whether for engineered applications, there can be a similar idea that in times of specific cyber threat, we can identify where an engineer might define a cyber attack surface to render inert, to do away with attack surface that exists within the system, and how they would staff to address the potential for a high cyber threat period. We're also conducting cyber-informed engagements with a number of asset owners and developing lessons learned from those. Ben, do you want to talk about what we're doing this year at our U.S. engineering universities?
Yeah, absolutely. So as we look into FY25, we understand coming out of 24, we have a curriculum guide. So many of our universities have begun to pilot those activities in their classes during this academic year, developing new activities. New universities are coming on and developing activities. And we have partnered with the Education Society with an IEEE to deploy a guide to curriculum, to CIE curriculum as a deliverable within that society, as another way to help codify what it means to adopt CIE as an educational tool to really allow engineers to interpret the modern engineering problems. But all that to say, all those activities, all those lessons learned will find their way into curriculum advancement and into a version 2 of that curriculum guide as we continue to refine the approach and make sure that it's goes through that continuous improvement process that's core to both the engineering practice, but just to quality outcomes. As we think about other avenues of getting this way to interpret these modern problems into our society, we think about centers of academic excellence that the NSA agency has has a relationship with many universities, what it looks like to have a CIE designation. But I think more importantly, especially considering this community, we think about what it means to become a professional engineer. We know professional engineers have a mandate to ensure their systems contribute and protect the public welfare and are engineered so that they benefit society and don't try to detract or have a destructive behavior in relation to society. And that problem is being challenged by the use of digital technology, not by the digital technology itself, but what the adversary is able to do with digital technology. And so cyber-informed engineering allows that direct response to say, even if an adversary is manipulating the digital technology, we have that engineered control to help ensure that the resilience of that system stays within the thresholds that make sense for the type of system we've engineered. And that becomes like a key addition to what it means to be a professional engineer in this modern age. As we think about assessing various technologies, universities have key laboratories that provide those type of functions. And so partnering with those labs to provide some assessment cases, what it means to do a CIE based assessment against various mitigation strategies, especially with the context of engineered controls. And then finally, allowing students to participate in a CIE focused competition. We have many various engineering competitions out there, but providing another avenue for more of a CIE centric competition so that this mindset, this way to interpret those problems is not only tested, but students can really explore what that truly means and come out the other side being more effective in how they've approached that cyber-informed behavior in their practice. So that kind of rounds out what we're focusing on for our education goals this fiscal year. So I'll hand that back over to you, Ginger.
Thank you, Ben. And then to round out our presentation, for our goal 3, we're focused on incorporating cyber-informed or continuing incorporation of cyber-informed engineering into international digital design standards. And in this case, we are trying to establish, for each standard, a CIE presence, because for many standards that have a very cyber basis, the application of cyber-informed engineering affects how they consider where risks might present. But often for engineering standards that very carefully govern the practice of the engineering discipline, how that cyber-informed engineering applies may result in what questions this engineer is asking about the potential risks that may occur and their awareness of the cyber relevance of a risk to the engineering function that they are performing. So by taking part in the governing bodies of standards, we're able to get the context we need to advise. We are working on a CIE standards white paper, which guides an exploration through application in a couple of standards, and a quick start guide that may help standards bodies gain enough understanding of cyber-informed engineering to identify places within the standard that it might apply. We're also developing some insight on process hazard analysis methodologies that are used, including LOPA and process hazard analysis, and there are several others, and how by changing which questions are considered by those process hazard analysis teams, the application of cyber-informed engineering might be incorporated as simply the expression of a hazard. We're also looking at use cases for cyber-informed engineering requirements analysis. So I'll stop here for questions and offer that certainly we'd love your questions here. If you have longer questions that you'd like to ask the team, you can reach us by emailing CIE@inl.gov. We've put many of the materials that we developed in the last 2 years into the chat, and we welcome your use of those. And there is the Department of Energy web address for the webpage that DOE has on cyber-informed engineering. So I'll stop here and ask, do you have any questions? It is our hope that this methodology could be incorporated into the engineering education provided to every engineer to enable them to incorporate the potential for cyber risk to engineered systems as a part of their routine engineering risk management and planning. Thank you. And George, if you're here, did you have any closing comments for us?
No, I don't. But again, I'll reiterate if anyone has any additional questions or if I can help in any way to merge these two communities, I'm happy to do so. And please reach out.
Thank you very much for your time today. We will produce a recording of this presentation if you'd like to share that and upload that to YouTube so that it can be distributed. And again, we appreciate your advice and your insight as we develop cyber-informed engineering about how to best incorporate it into the engineering discipline. And yes, we will send the links to the resources with the recording and the slides.
Yeah, Ginger, if you don't mind, I'd like to say some parting words as well. So many of you I know sit in various societies and have spent a time designing control systems for the Navy. And so when I think about cyber-informed engineering, the real power that it comes to hold is when I'm thinking about a certain control problem and I design a PID controller to solve the dynamic that I'm seeking to control. The risk that cyber now presents is, can I even trust the solution I built? Because I've deployed it in software in a controller, and that controller now has a network connection to deliver the state information, deliver the status up to human machine interfaces and to databases and things of that nature. And so as adversaries find their way into the infrastructure, find their way into the controller, have the ability to manipulate that PID, I'm left with the question is, what can I do if I no longer trust that solution that I built? Can I look for additional mitigations to at least guarantee a minimum set of performance or safety or reliability for the critical application I've designed it in? Obviously, not all applications require the same level of robustness in the solution, but especially for our critical infrastructure, this requires that additional thinking that I think traditional engineering hasn't come into because we're focused on making sure the system operates, and but this provides that other mechanisms to interpret those challenges for this modern age where the idea of trustworthiness wasn't necessarily a concept we worked in initially, but is now prevalent by the fact we're using digital technology. And I think us as engineers are the right audience to seek to address that problem and think about how we can modernize our solutions to overcome those risks, that digital risk that's now a key component. Because of the fact digital technology is really in almost every component now that we select. even as I think because we're Department of Energy in the energy systems, the idea of the digital substation is a perfect example of that reality. And how can we respond to that with our practice of engineering to complement the world that cybersecurity is seeking to do to ensure that the digital, that data domain has the utmost security practices in it. So I thank you for the time as well. And I'll hand that back over to you, Ginger.
Thanks, Ben, and thanks to all who attended today. We will provide resources and look forward to further contact with you soon. Thank you.